You know when you're playing a video game or watching a big blockbuster movie and the 3D graphics look so real? The way the light hits a character's face or rolls across a landscape? Ever wonder how they do that? Well, it's not magic, it's math. And the secret really boils down to three incredibly powerful, and actually pretty intuitive, ideas from vector calculus.
So here's our game plan. Think of this as our roadmap. We're going to start with a really simple idea, a hill. And then, step by step, we'll build up a powerful conceptual toolkit that's going to let you see the world from a completely new angle.
All right, to make all of this feel real, I want you to imagine you're a hiker. You're standing on a beautiful, rolling hill. Got it? Okay, because this hill is going to be our guide for this entire journey, helping us visualize some ideas that can feel a little abstract at first.
And here we go. This is the first big idea. That physical hill you're standing on, with all its curves and slopes, it isn't just a random shape. We can describe it perfectly with a mathematical equation. Every single point on that hill has a precise location we can map out. And that's the bridge, right? Between the physical world and the world of math.
So you're on our hill. Now, here's a question that sounds simple but is actually pretty deep. Which way is up? On a curve? That's a fascinating problem. And this brings us to our very first key tool.
I mean, if the ground is flat, up is easy. But what if you're on a steep part of the hill? Your personal up is totally different from the up for someone on the other side. So we need a really precise way to define the direction that's pointing straight out from the surface, right at the spot where you're standing.
And here's our answer. It's called the unit normal vector. Let's break that down real quick. Vector just means it has a direction. Normal is a fancy math word that just means perpendicular. And unit? That just means we standardize its length to exactly 1 so we can focus only on its direction. That's it. And here's a way to picture this that makes it all just click. Imagine at every single point on that hill, you could plant a tiny little flagpole. And that flagpole always sticks straight out, perfectly perpendicular to the ground at that exact spot. That little flagpole? That is the unit normal vector. And this isn't just some abstract thing for a textbook. Remember that video game we were talking about? The computer is calculating the normal vector on millions of points on a character's face to figure out exactly how light should bounce off. That's what creates realistic shading. It is absolutely fundamental to our digital and our physical world. Okay, so we now know which way is out from the surface. But what about moving across it? I mean, as a hiker, you're not just going to stand still. We need a tool to describe the steepness of your path when you start walking.
So you're on the hill, and you decide to walk, let's say, 30 degrees to the northeast. You're not going straight up the steepest part, and you're not walking along a flat path. You're going at an angle. So how steep is that specific path? How fast is your altitude changing right at that moment?
Now, you might remember the basic derivative from calculus, which, measures the rate of change. But a standard derivative is kind of limited. It usually just measures change along one axis, like if you're heading due east. The directional derivative, though, this is a whole other level. It's like having a special compass that can measure the steepness for any direction you point it in.
So think of it this way. It's the instantaneous slope of our hill, but not just up or down. It's the slope in the precise compass direction we choose to travel. It gives us a complete 360-degree picture of the landscape steepness right around our feet.
So we've got two fantastic tools in our kit now. The normal vector, which tells us which way is out, and the directional derivative, which tells us the steepness across. Now, let's combine them to solve a really interesting and kind of tricky problem.
Yeah, think about where two different surfaces meet, like two sand dunes blending together, or the way a car's fender curves into its hood. How in the world do we define the angle of that intersection? It's not a sharp corner. It's this smooth, flowing curve.
And that's the real problem, isn't it? You can't just put a protractor on it. Along that line where they meet, the angle is constantly changing. It seems like it would be impossible to measure at any single point. But the solution, oh, it's beautiful because it's so simple. We don't have to look at those complicated curves at all. We can use that very first tool we put in our pocket, those little flagpoles. And this right here is the big aha moment. It's such an elegant idea. At any point where two surfaces touch, each one has its own normal vector, its own flagpole sticking straight out. The angle between the surfaces is defined as the angle between those two straight, simple flagpoles.
We've just turned a very difficult problem about curving surfaces into a super easy problem about the angle between two straight lines.
And that is what makes math so powerful, finding these clever ways to make complicated things simple.
So let's just zoom out for a second and recap what we've built. We started with this simple image of a hiker on a hill, and we ended up solving a genuinely complex geometric problem. Pretty cool.
Here's the toolkit we put together. First, we understood that surfaces are just landscapes defined by equations. Then, we figured out the straight-out direction with normal vectors. We learned how to measure steepness in any direction with directional derivatives, and finally, we applied that first tool to solve a new problem, finding the angle between two surfaces.
And I've got to say this again, these ideas are not just for an exam. They are being used right now, as we speak, to design airplanes, to simulate weather patterns, and yeah, to render those incredibly realistic graphics in the movies and games we all love. So it all comes down to just three core ideas: defining a surface, finding a direction pointing out from it, and measuring the rate of change as you move across it.
And that really is the essence of vector calculus. It gives us a language to talk about all the flowing, curving, three-dimensional stuff in our universe with absolute clarity and power. It reveals this hidden mathematical structure in everything around us.
But that leaves us with one last really tantalizing question. As our hiker, standing there on that hill, you can now calculate the slope in any direction you choose. But of all the possible paths you could take from that spot, which one is the absolute steepest? What's the path of maximum ascent? Well, that is a fantastic question for our next explainer.